If you are designing PCBs, then you probably read some articles on internet which are talking about some small things which can influence quality of the signals on your PCB. Small things like unused part of a via or via stub. Maybe you read that this can influence quality of the signals in your PCBs. Or maybe you read some articles that also the structure of the fiberglass inside of the prepreg or core can influence the quality of the signals on your PCB. Or maybe you read also the articles about copper roughness. You know, the surface of the copper is not always completely flat. Sometimes there are these small bumps, and they can influence the quality of the signals in your PCBs. And maybe you wondered, like, but how much this can influence the signals? And also, maybe when you need to start considering these small things in your designs. And that's what we are going to talk about in this video. And also we are going to have a look at some examples. So you will see, for example, how this unused part of a via can like completely damage signal. It's supposed to be this kind of signal, but because we have this via stub, the signal is like completely damaged. And you will see also some examples on the other small things. So I really hope you will find this video interesting, and I really hope you will find it useful. I'm not an expert for these topics, and it means, as usual, I made a call. This time I talked to Bert. We recorded this call, and that's what you will see in this video. If you would like to know more about Bert's work, you can visit his website, and here you can find a lot of information what he has been working on. Okay, that's enough for introduction. And Bert is going to start our call with explaining what is behind of the problems with this via stub. So on this picture, you can see a through hole via, which is starting, for example, on top layer, ending on the bottom layer. And the signal is routed from the top layer, and it continues somewhere in the middle of the PCB. So basically, this part of the via is not used, and you will see why this is a problem, or when this can be a problem, and what it can do. So let's start my call with Bert. Here it is.
If you have like a signal at a certain frequency, it goes into the top of a via. And as the signal goes down, it splits. So part of the signal goes along the trace, and part of the signal continues down the via to the bottom. And when it reaches the bottom, the signal reflects back because that's open circuit. And the signal kind of goes back up the via again and splits again. So the length of that stub is what they call a quarter wavelength of your main frequency of that one signal. And when it goes down a quarter and comes back a quarter, you've got a half a cycle delay of the signal. So your blue signal is gone, and then 1/2 cycle later, you get the same a portion of that signal back. And that combines with that signal, and you get a very low signal afterwards. Okay, so this is an actual measurement of with the S parameters.
Mm-hmm.
So this is a measurement of a backplane sort of channel or structure, and it had a stub length of 270 mils. So it uses a vector network analyzer or a VNA to get the S parameters.
And
it really sends all these different sine wave frequencies, right up to 20 gigahertz here. So each point is a certain sine wave frequency.
So you had a PCB
right.
with 270 mil stub
yes.
in the via. You had a
yes.
track, and then you measured properties of this structure.
Right.
And this is the graph. And it basically means or does it basically mean that if you have signal like 8 gigahertz, it would work perfectly fine with this 270 mil stub?
No.
I apologize for interrupting, but I would like to be sure everyone understands what we are talking about. So basically what we see on this graph is loss for different frequencies. Okay, you know that when you are running digital signals through your tracks, it is actually not only one frequency, it is multiple frequencies in this signal, because square signal continues a lot of different frequencies. And from this graph, you can very nicely see which frequencies are going to have problems with this kind of stub, what we can see here. So for 270 mil stub and for 4 gigahertz signal, you will have a lot of loss. It means if you put 4 gigahertz signal here, then on this track there will be a much lower 4 gigahertz signal continuing down this track, because you lost a lot of signal because of this stub which is here. And that's what you can see from this dip which is here. Okay, for a little bit higher frequencies like this, the loss is going to be a little bit lower, but see what we are going to talk about, and then you can make your own opinion if this is good or bad. Bert is going to explain basically what you need to have or how this loss should look if you still would like to keep good quality of your digital signal. Okay, we can continue.
You don't want any resonances near your bit rate that's happening. Even though it shows things here, this stuff could affect other things.
That's what I think, yeah.
You really don't want any resonances there. Typically, you want any resonance, if you measure your channel, you want your first resonance to be at least 5 times past the Nyquist frequency of your bit rate that you want. And here, this eye here shows the first resonance is at 20 gigahertz. And this is a 65 mil stub. And you can see, well, we've got a pretty open eye at 10 gigahertz there, right? So that means 10 gigahertz or 10 gigabits per second. We got about 10 dB of loss, or 9 dB of loss at half of that, right?
So how much loss is acceptable usually?
Well, that depends on a lot of things, right? At the end of the day, it matters is how open your eye is. As we go up in the bit rates these days, there's equalization and things that compensate for the losses. So even though you have a channel loss kind of showing there, the SerDes, the silicon, has equalizers to open the eye up more.
Wow.
So loss is important, but the silicon these days can take that into account. What the silicon can't do is something like this, right?
Yes.
We have the resonances. So, like for a backplane channel, like a lot of the specs, they talk about 30 dB roughly from chip to chip on one board to the other through a backplane. And depending on your material and a lot of factors, that can be different lengths. If you have really good material and done your homework and done good design, it might be around 30 inches at like a 10 gigahertz, for instance. At 28 gig, it's probably less in lengths, right?
Okay.
It's really the loss.
So let's move to the next slide. So this is a really nice picture because it shows, or very nice graph, because it shows that for standard PCB thickness, like 63 mils or 1.6 millimeter, we don't really need to worry about some back drilling up to like 2.5 gigahertz or 5 gigabaud.
Yeah.
That's like PCI Express, or what is it?
Right. Yeah. So, for instance, at 5 gigabaud rate, it's 2.5 gigahertz, right? But 5 gigabaud is like PCIe 2, right?
And what is the more faster PCI Express?
Well, Gen 3 is 8, Gen 4 is 16, Gen 5 is not on here, but it's close to. Gen 5 is 32 gig, right? So certainly, depending on what layers you are as well on your board, the point is where you put your high-speed layers affects your stubs. So, if you have a 62 thick board, if you put all your high speed on the top, then you might have to back drill, right? If you have it partway in the board, if you choose your layers near the bottom or in the middle, you're only about 32 mils, right? So you're probably okay for, the mid-range there on your board.
So does it mean that if you have this kind of very fast interface, it is better to actually go on the bottom side and then continue with the signal, or the problems inside of the VIA are equal or even bigger than the stubs would be making?
Well, your VIA is affected by mainly your anti-pads of the plane layers, the clearance holes in there. That affects your VIA impedance. And what we want to try, like any sort of transmission line, we want to have matched impedance all the way through. So you have to carefully kind of design your VIAs. So VIAs in and themselves can be made fairly transparent, in a design somewhat.
So if you use proper VIAs, then for very high speed signals, it's actually better to go down on the bottom layer than continue.
You can, but you don't always have that luxury because you have several layers. So every signal can't go to the bottom. But in principle, yes, there's some kind of loss kind of going through, and you need proper stitching vias, of course, to kind of go through all of this stuff. But if that via is designed properly, it should go through. It will have an effect. There will be some loss in the via, but not huge, right?
So the best is just route on the layer where the components are. No vias.
Well, that would be in a perfect world, but we're not there. Yeah, PCIe cards are very challenging these days. They're 62 thou thick, and you've got all these you got transmit and receive, so you got to watch the crosstalk, and you have to change layers to cross things. Everything just doesn't always flow nicely, as you're aware. So, okay. But really, what really is the problem is the stubs at high speed. So you want to eliminate stubs lengths as much as possible.
My biggest worry was always like, when do we need to do the back drilling? Because normally I don't see it almost on any boards, but internet talks about back drilling, so I wasn't sure when I should start be worried for what kind of signals or for what kind of speeds.
Yeah, so that's where this table kind of helps,
Yeah.
right? Using the Saturn tool, if you know your geometry, all that stuff, use the DK of what the data sheet shows on your stack up. That's what the red means. So, you know, at 1 gig, for instance, no big deal. But as you're getting to 28 gigabaud, like for PAM4, 56 gig, for instance, or 28 gig, that's why I put these two, because they're the highest rates we're kind of working in the industry now, you know, kind of in production. So it sort of says you have to back drill.
Can we talk a little bit about this NRZ and PAM4? Because I didn't understand what is basically the difference. It is in the shape of the signal. That's the difference?
Actually, with NRZ, non-return to zero, you have a 0 or a 1, right? It's just 2 levels.
Yes.
0 or 1.
I see the 4 levels in
Yes.
the other pictures.
Yes. And with PAM4,
I didn't know they do it this way.
exactly.
So you can actually then transfer much more data.
Right. You have 4 different kind of codes, right? Or
which
4
you can
different
transfer
levels.
in one transfer, basically.
Yeah, it's like you get 2 symbols, what they call symbols per bit time. And that's why PAM4, you know, you get kind of double the information sort of in 1 bit time.
Yeah,
right?
I understand. That's cool. I didn't know. I really didn't know it worked this way. So that's why you have 3 eyes there, basically.
Yes, exactly. For the 4 levels. So you've got 3 eyes. This is 2 levels, so you get 1 eye, right? So here's your 4-0. You got this mid and then the upper range. So, you know, within 1 bit time, you've got 2 symbol rates, what they call in it.
In the top one, you get 0 or 1, but in the bottom one, you can get like 0, 1, 2, and 3.
Right.
Or
so
more?
You know,
I don't know.
Now that we've gone to PAM4, really we should be going away from calling this NRZ, but NRZ has been used forever because that's all we had. This is really PAM2. Okay, 2 level PAM2.
And PAM4 is used where?
PAM4 is used for really anything that's, well, anything past 28 gigabit or gigabaud rate is going to PAM4. Now, PCI Gen 5 is still going to NRZ. So when they're going to the next gen, they're going to go to PAM4.
Okay.
Right? That'll be 64 gigabit, right? It'll be PAM4, as my understanding. So really, you're running out of stuff. And then the next generation is, they're talking 112 gig, right? And they haven't sorted out that yet. If it's PAM4 or PAM, other PAMs, right? It just gets more difficult as you go up in it. And so people have different ways of achieving that rate. But the PCBs is kind of running out for long lengths at the higher rates. It's getting more challenging. So that's why you're finding some what they call flyover cables, you know, to has coaxial cables as jumpers to kind of, you know, spread the gap at the higher rates.
Let's move to other slides. What do you have next?
Okay, so I'm just going to go through. We talked about the vias. Before we leave the vias, I have a couple of more slides. That, this is sort of like what backdrilling kind of happens, right? So in this picture here, we have a differential via or 2 vias, and you have the top, and then you have the layer here near the top. And actually, this is the cross section of that long via that had the thing closed, right? We measure it. If it has a via stub that's that long. So what backdrilling does, you know, the drill back drills up, and usually like the back drill size is 8 to 10 mils over the drill diameter on it for proper back drilling. But things you have to consider is there's drill wander. So usually they make the anti-pads a bit, larger to account for any kind of wandering. You can see these are actual pictures of a cross section where the back drill is pretty solid, but it can wander over the thickness of the board. So you're really saying you may need larger anti-padding. There'd be trace implications and all that stuff because of it.
So you need a little bit bigger gap.
Right. And that's usually defined by your board shop. They kind of tell you like copper to copper spacing they can kind of deal with for back drilling.
Or back drilling to copper spacing.
Right. And like high-end board shops can back drill to within 5 mils of the layer to keep sort of thing. So you specify that in your fabrication notes. So it's usually 5 to 10 mils for on there. So the very high-speed boards, you're ending up with roughly 10 mil drill, and 10 mil stub. And with a 10 mil stub, you're pretty good with 28 gigabaud stuff. So boards we're designing now, board shops can deal, but of course some board shops can do better than that. But usually that's what it is. For these data rates, you have to go to a higher end board shop to deal with it. They have to deal with stuff.
But still, it's very impressive to actually drill within 5 mils.
Yeah, well, they've got the technology. So this is another thing with back drill versus implication with press fit connectors.
This was one of my thinking like, why should I back drill when if I use through hole connector, then the pins are going to be connected from top to the bottom, but that's not how it works, correct?
Right. Yeah. So what you'll find for high speed, especially backplanes are big for this. Backplane connectors are pretty much almost always press fit connectors. So this is like the header that goes on the backplane, and this is the mating connector that would go on the card that would plug into the backplane. And all of these things are either press fit, or the one on the board may be kind of a surface mount, but the ground pins are often press fit as well. So what that is the actual pin looks something like this in a cross section.
So the pin is not 1.6 or 63 mils or more long. Pins are actually very short.
Yeah, for high speed, they're short, but they do need a minimum via barrel length, for reliability and to make proper contact. So every connector manufacturer have their own pin style. They all work pretty much the same, but they all sort of specify what the minimum via length that you need. And if you have to back drill for high speed, you have to make sure you have that via length left.
So to introduce this topic, basically for high speed, for these very high speed signals, is important everything what is on your PCB. And it includes also quality and properties of the material which is used to manufacture the PCB. And on the PCB there are usually two kinds of materials. One is the copper and the other one is the prepreg.
Right.
So what is important for these very high speed signals to consider when you are choosing these like prepreg or core materials? Yeah,
so the big thing as far as the dielectric material for high speed is the woven glass style. So here you can see examples of the fiberglass weave inside the laminates or the prepregs. And, they have different numbers associated with it. And like a 106, 1067, 2116, they're sort of standard weaving numbers, and they're all outlined in this IPC spec, but really means is this style is a unique number. Like 106 means it has a warp and a fill spacing of 56 kind of mil or 56 threads per inch and 56. So this 106 is 56 threads per inch going along here.
I understand.
And it gives a certain thickness of the actual laminate itself. So board shops, they have a DKDF table. They have different thicknesses of prepregs and cores, and they'll have different glass styles, what they call.
So basically, if you go for 3313, then the minimum thickness is like 3.3 mil. That's quite low.
Right, exactly. Right, and then they build laminates. So if they want a 6 mil laminate, they'll say use 23313.
But then you will have the layers further away from each other when you use this.
Yeah, exactly. So it depends what stack up you want, and they have the tables in the each laminate supplier says, I'll give you a 4 mil thickness, and it includes whatever number it is. So, all these numbers are related to get your thickness to build your stack up. But for high speed, we're worried about kind of skew, what they call a fiber weave effect. But you can see here in 106, you have the glass bundles, but we also have these open windows here, which is resin content in there. So we have 1067 is what they call a spread weave. They actually spread out the fills direction, and it kind of makes it more uniform in it. They do that. It wasn't done for high-speed signal integrity. What they've gone to this spread weave glass was mainly because of high-density interconnect in microvias with the laser drilling. They wanted more of a consistent material for it. So that's why you see the spread glass. It was for really microvias and HDI technology, but it helps us in the high speed area as well. I can talk about fiber weave effect in it. But the big thing to take away from this picture is there's different glass styles, different weave patterns, different thicknesses, and different pitches, distances between these things.
So how this is important?
Yes, it's important for fiber weave effect, actually. So, and fiber weave effect is what it means is if this is sort of like hypothetically, say it's like a 106 type material, non-spread, you can see that if you have a differential pair, if one trace of the differential pair is routed mostly on the fiberglass strand, and the other pair happens, because of the spacing between, happens to land in between, you're going to get a difference of decay that this trace sees versus this trace.
And decay, it means the speed of the traveling of the signal will be different.
Right, essentially, right. And that's kind of calculated here, dk max and dk min. So dk max will be over the glass, and dk min is mostly over resin. And you can calculate the skew, how much timing skew you'll end up with, quite simply, if you kind of know the two dks. That's kind of hard to know, but you'll end up with skew. So fiber weave effect has to do with skew.
It means the edges will not travel together, but there will be some shift.
Right. And that's sort of what I'm going to show here. If we have a signal, the plus and minus, if they're perfectly lined up when they start off at the transmitter, they go there. The differential signal is twice the height, and there's no conversion between differential and signal. So the common signal is flat. So when you end up with skew, means one, the D plus will travel faster or slower because it's on the higher decay travels at a different speed than the minus. And that's sort of shown here, the D plus and D minus. And what happens is your differential signal gets distorted in here. It gets smaller. And your common signal increases. So the more and more skew you have, eventually your eye is going to be totally closed on it. So skew is quite important thing to consider.
When do we need to consider this? Again, for what kind of frequencies or bow rates?
I'll get into that for a second. So I want to kind of show the effect if you don't kind of consider skew.
Okay.
Here's like a real world example of things. So for 1080 glass versus spread weave glass. So here is two different stack ups. It's exactly the same design. And we actually built like a test, kind of a demonstrator backplane a few years ago. We built it with 1080 glass of Nelco 4013 EPSI at the time. And it's kind of shown they're just 1080 glass, which has open weave patterns in it, versus 1035, 1078 in Meg 6, which were spread weave. So we measured sort of like the impedance here. This is showing the TDR. So this is the TDR plot, the impedance plot of the plus and minus of a differential pair. And we end up with a skew of like 6 picoseconds on it, just because of the way the board was designed. So
at the end, you can see the shift, or how did you come up with 6 picoseconds?
Right here, if you measure it, you can see that
there is the shift.
It's the shifted.
Yeah.
Right. One is arriving faster than the other one.
Okay.
Okay. And this is a time TDR plot of the impedance plot of that channel. But regardless, you can see that it's varying. They're not even. It's kind of they're not running the same all the way through on it. Now that's the important for that slide. But when we use the spread weave thing here, you can see things are much more controlled, right? Each one is kind of following each other. And in this case, there was 0 picosecond, right? It's very low, right? We couldn't measure it. But that's just the difference between spread weave, what it will do, versus the other. It helps to control the skew on there. So how much skew is important? Well, it kind of breaks down to sort of this picture here. Generally, we have a skew budget. When we talked about before, going back to like via resonance, skew causes a resonance as well. So they're kind of similar to via stubs. So in your channel, you generally budget 20% of the bit time of your channel for skew, total skew. That means fiber weave effect, any skew in your system. So here's an example at 28 gigabaud, your UI is about 35 or 36 picoseconds wide, okay? And 20% budget of that is like 7.5 picoseconds, right? So that's your total budget for skew before it starts affecting closing your eye. So in this example, with following the IEEE spec, that's the black line. The red line is our insertion loss channel. We're above the spec, we're okay. And we got an open eye at the other end of the thing.
So this would be what frequency?
Well, this is like for 14 gigahertz.
14
right?
gigahertz, okay.
But this is the whole channel up to 30 gigahertz, right? They have a specification. Your insertion loss has to be above this black line. So here we're meeting the spec fine. Where everything is good. We have an open eye. There's no skew, 0 picoseconds of skew. So if I introduce 7.5 picoseconds, which is this 20% UI, you can see we're not the eye is pretty much the same. We just started to, affect the eye. And with PAM4, it's worse than NRZ because the 3 eyes makes more of a difference. But you can see here, the eye is starting to close and the insertion loss is getting closer to the spec here. And if we end up with 14 picoseconds, like double, we don't meet the spec and the eye is pretty closed, right? So for the higher speeds, like, this 28 gigabaud rates and PAM4, skew is really, really important to factor. So you have to make sure you're cognizant of it all. Use the spread weave glass, and depends how you route things.
How did you come up with this red line?
The red line is a measurement.
A measurement of which of the signals?
Oh, it's the measurement of your channel.
Channel, okay.
That's your channel.
So it means that's the combination of the plus and minus signal or different signals.
From one chip to the other, basically.
Okay.
Yeah, so that's the whole length of your routed trace on your board. So that's the loss of your trace, really.
So you can measure also loss of differential pair signal?
A differential pair, it has 2 traces. So,
yes.
So the VNA, probes those 2 traces, at one end at the other. So you have like 4 ports on the trace. So 2 at the input and two probes at the output.
So you measure them together?
Yeah. The VNA does the whole measurement.
Oh, I didn't know you can measure differential pair with VNA. I thought you only can measure like single-ended signals.
Oh no, VNA, they have it like that's what they call a 4-port VNA.
Okay,
and then
from this measurement, you will get this red
yes, exactly. That'll be the loss of your channel.
And the red graph is also telling you basically where are the resonances. For example, in the first one, there is like 20 something gigahertz.
Yeah, they're not deep, right? Mm-hmm. They're just little discontinuities affecting it. And that's why they have this limit line showing, they're accounting for things like that. So any resonance or any dips should be above that line for the channel. And, that's part of this 802.3 specification.
This is interesting because now we are talking about loss, but how this loss is connected with the shift.
Well, that goes back to, where I talked about when you have skew, the differential, the conversion happens.
Okay,
right?
So it is all, basically this graph includes also the skew.
Yes.
Okay.
The skew is causing this loss, more loss.
Okay.
Right? Because what's happening is the skew is causing that resonance. You can't see it in this dip, but here there's no skew. So that big dip is, way out in frequency, right? But as you're having skew, you're going to get that dip getting closer and closer. And you can see this shape is kind of going here. So now you got to, we're not going further. The dip is about probably around 25 here. We don't have the full scale here, but there's more of a dip happening, maybe further out. The important thing is skew affects your insertion loss of your channel. And that's shown here on these top graphs. And here's what it's doing to your eye opening.
Okay. Because, in my head, I knew that if you have different skew, then it's going to damage your eye. Because, the edge can go in different times. But I didn't know it's basically same as when we compare it with this loss. It's interesting. Everything is connected together.
It is. Absolutely. I go into the things in more detail with the via stub resonance, in one of the white papers on my website, goes into that theory, but it's all connected is right. So, resonance, that's why we want that first dip resonance to be 5 times away from your
because
thing.
it affects basically whole line.
That's where this 20% UI comes in. With 20% UI, that first resonance will be 5 times away from your Nyquist frequency, really.
It's kind of pulling it down the whole
Exactly.
characteristic.
Right, exactly. And at 14 picoseconds, it pulled it down even more, right? And that resonance that was far out before is being pulled closer and closer to the 14 gigahertz. Even though you're not totally dipping at 14, you can see that the loss is now, past this margin here. It's like, what, 17? No, it's about 12 dB. Down here, 13, 14 dB, and look what it's done to the PAM4i. PAM4 is the worst. PAM4 is most critical with Skew. You can see we've already lost almost 10. What is this? This is that's the height, 10 millivolts almost. Let's say 8 millivolts in height, and the width, we're getting narrower in the eye widths here.
But do you know what interface is using PAM for?
Any interface that's running.
Do you know like a specific one?
Well, 802.3 is the Ethernet standard.
Ah, okay.
Like for Ethernet, and they have the OIF is, they have a standard. They're very similar. Like this BS code means PAM4 channel stuff. So anything that's compatible with 802.3 or Ethernet has a spec, and for PAM4 it's the BS. PCIe has their own spec, of course, and they have different requirements and things.
But you say right now they are running on, they are not using this one.
No, but it means the same thing, same idea, right? The only thing is with the 2 level or NRZ, it's probably, you have a bit more margin because it's 2 level.
Yeah, definitely.
Right. So, but this gives an indication of 7.5 picoseconds. That's total skew now. That includes fiber weave effect. Any other skew, like your trace lengths aren't matched in lengths, that'll cause skew. If you don't have symmetrical return vias between the P and N, you'll get a bit of skew. Your breakout, if you have, from your BGAs and stuff, if they're not sort of symmetrical, anything that causes asymmetry in your physical differential pair will cause skew to some extent on your board.
And that will cause insertion loss.
Exactly. More skew. The insertion loss, it gets a little lower on it. So
okay. What do you have on the next slide?
Yeah. So that was there. So mitigation techniques that people do for fiber weave effect. Well, the first thing is choose a spread weave glass style. Many of the high-end laminates that have low dielectric loss already come with spread glass weave, but it's always good to check with the laminate supplier what it is. This always happens as my phone rings when I'm on a video call, but it's going to
we can wait.
Yeah, so that's okay. Sorry about that. Anyway, so that's one use spread weave glass style is.
So mitigation technique, it means how we can kind of
prevent it.
Okay.
How prevent skew, or to make, to prevent fiber weave effect. Another way to do it is what they call match the differential pair routing pitch. So you choose your spacing of your differential pair.
This would be risky, I think.
Well, it is, but If you like those glass styles that I had, like 106 and everything, they have the threads per inch, and you can calculate the actual pitch between the bundles in the weave pattern with it. So it's easy to find that out. Each one is. So if you use 1035 glass, for instance, I think it's a 15 mil pitch.
But then if these are like differential pairs, then it would be hard to actually.
Well, it is. It is. But if you can do it, that's one mitigation technique. So sometimes you can do it, sometimes you can't, right?
Interesting.
So
yeah.
Certainly spread weave, if you can do it, that's going to help. Matching the diff pair routing pitch, even if you have spread weave glass, will help, because each spread weave has a different pattern depending on the style. So that's one way of doing it. And then the other thing is what they call zigzag routing. Like they generally do this about 7 to 10 degrees over certain lengths. That's techniques that people do. And then other things is rotating the panel itself, right? People rotate the artwork on the panel.
So again, you rotate it 7 to 10 degrees.
Right. And that's like, but that adds extra cost, of course, because material costs more waste with it. So those are some of the techniques. Spread weave might be enough. Matching the diff pairs, if you can do it, might be enough, but you can't always do it, because breaking out of your BGA, you're not going to be necessarily on the pitch, right? So, but you can change the widths, the geometry after you break out if you have long lengths, right, on it. But sometimes you use a combination of these, right? It's no one rule of thumb that says you just do this and it'll be okay, right? So that's it for like material properties from the dielectric end. As far as
but that's not the only material what we use on PCBs,
right? So it's this is the conductor roughness. For high speed, we have to be concerned about it. In the real world, there's no such thing as perfectly smooth PCB conductor surface. We've always had roughness applied to promote adhesion to the dielectric material. So for years, the rougher the copper, the better it was for peel strength, the whole bit. But the higher speed you go, now the rough copper starts to affect your loss of your channel as well.
And the reason is because the currents will be, for very high frequencies, the currents will be traveling basically only in the very surface of the copper.
They're called the skin effect.
Yeah.
The skin effect. So, so failure to model the roughness can ruin your day. Here's the insertion loss plot, for instance. In red is sort of a measured loss and simulated loss. So if we didn't model it correctly in our simulation prior to building the board, we didn't factor it in properly, we could end up with surprises when we get into the lab. And here's an example of an eye opening that we simulated in with smooth copper. Had a nice open eye, it seemed, in the middle, and everything's there. But when actual measured channel, the eye is
much smaller.
It's closed, smaller, and that's only like 3 dB difference at this Nyquist frequency at 12.5 gig. 3 dB, you got half an eye height opening.
So in simulation, we may think like, oh, everything is okay.
Yeah, that's exactly right. So these are the things that we have to look out for when we're doing high-speed design and modeling and simulating, especially the modeling. We have to have good models, right? And
so you can actually add these roughness into your simulations?
Yeah, exactly. So why is loss important? Is going into the IEEE 802.3 BS spec, they define this chip to module spec. And here's your one chip on, say, your motherboard or your board. and it has to go to a module, which is like a plug-in module for optical modules. They plug into these things. So the total loss of that channel from one end to the other is, 10 point something dB, 10 and a half dB roughly. And in reality, we have like these server kind of cards, they call them like pizza boxes. They're about 17 inches wide, and they go on the rack into the customer premise. These are networking kind of routers, like Cisco routers or things, right?
Just small technical question, like, okay, so there is the module, and then there is chip, which is far away from the module.
Yeah.
Okay. And you need to connect the module with the chip.
Yep,
Okay.
exactly. And the budget that you have is 7.5 dB, right? For that part of this budget here.
And do you know how it's like 10 inches it can be or something?
Well, that depends on how wide your traces are, what material you've used.
But how far usually you need to route from the module to the chip? So what kind of distance we are talking about?
This could be, realistically, if you have one main switch chip in the middle here, and a module is right at the edge, kind of here, it could be, 8 or 10 inches long, depending on the placement, right, of it, and depending on what your line width geometry is and the material properties you use. It's challenging to meet all of this stuff. So you have to model it correctly, choose the right material, and model the roughness properly as well.
Okay.
So, so what is roughness itself? How they measure roughness in the industry, they use what they call a proliphometer. It's a mechanical device. They have the sample of the copper.
How they call it?
A proliphometer.
Okay.
It's I didn't put the name on it, but it's called a proliphometer, and they measure it. And what they do is they have the sample, and they just drag a stylus, just like your record player had a stylus to play back the recording. There's a stylus tip that gets dragged along the surface, and as it gets dragged along, the profile of that surface gets recorded on it. So it's a two-dimensional roughness profile that they measure. And what you'll find on data sheets are like RMS roughness and average roughness and RZ. So there's RQ, RA, and RZ numbers. RQ is RMS, RA is average, and RZ is what they call 10-point mean number. But the 2D roughness profile is denoted with an R and a subscript. When you see an R and a subscript, it means it's from mechanical proliphometer.
Oh, I think, and that's the number what you add into simulations?
Exactly, exactly. So that's why the RZ numbers are important, mainly the RZ. But these are the numbers you'll find on data sheets, typically. You'll find different places on a data sheet, you'll have these numbers. So this is how the electrodeposited copper fabrication process happens. They have a large drum made of stainless steel or titanium, very smooth, and it's partially submerged in a vat of copper sulfate solution. And the drum is slowly rotating, and they've applied like a voltage between the cathode of the drum and the solution. And as it's rotating, the copper gets deposited, electrodeposited from the solution onto the drum itself as it kind of turns, and gets peeled away and then gets coiled up into the spool. And it's important to know there's two sides of the foil in electrodeposited foil. They call it drum side of the foil, And that, of course, is contacting the drum. And then the matte side is the side coming out of solution.
So the drum would be like smoother, I guess.
Yes, exactly. The matte side is always rougher than the drum because the pattern of it gets deposited onto it.
Mm-hmm.
And the speed of the drum controls the thickness of the copper. So they work all that out to it. But this is at a very high level kind of concept.
I was just thinking like how easily it may be like pull away the copper from the drum.
Oh, they've got that worked. It's probably like stainless steel.
It's not going to stick there, yeah.
Yeah, and depending on the material, so it's very, very smooth on it. So here's like a common electrodeposited roughness profile. So coming off of the electrodeposited process, there was sort of like years ago, no min-max spec. That was sort of the pattern of the matte side that was coming out of the solution picture. So there is no spec. The IPC along the way have developed a spec for a VLP type foil, copper foil. And this is sort of like the profile of a VLP foil. And they were having like roughness of RZ number less than 5.2 microns maximum for it. So for a VLP was less than 5.2 microns. Mm-hmm. But now we have the ultra low profile class of foils. And there is really no IPC kind of standard in the industry. You've got people calling it HVLP, VLP2, God knows what. Everybody calls it differently. But generally, if you talk about what the roughness numbers is, it's typically these ultra low profile classes are less than 2 microns maximum.
So how they are going to stick it together if it's so smooth?
Well, that's always the challenge, right? On inner layers, you're not as worried as much about the peel strength as you are on outer layers. So, on inner layers, you'll probably be dealing with
because they are all good together. Then in inner layers, you are not worried.
Yeah, you do need roughness, but it's not. You don't have to be the concern of the peel strength like you do on outer layers. Mm-hmm. So, but generally, for high speeds, you want to choose a smoother foil. And you want to go ultra low profile class. And they do have that. Laminate suppliers offer it, for the high speed. So that sort of shows what the foil looked like coming off the drum, each side. So here's another kind of picture. A matte side is rougher than the smooth side. So the drum side this is the pattern of the drum itself, fairly smooth, no ridges or anything. But what they do is they go through a nodule treatment process where they want to add additional little tiny nodules onto the treated side of the foil, what they call treated side. Usually most of the time it's one side of the foil, and most of the time it's on the matte side of the foil. Mm-hmm. They want to add little tiny nodules. And that's what it looks like on the matte side. These tiny little nodules are kind of put on. And that adds micro roughness to it. It actually increases like the surface area, so you get more bonding to it. So,
what kind of material they add there? Is it copper? No, it doesn't have to be copper.
I don't know. It's different. It's a treatment, right? That's
okay. So it's not copper. It can be something else.
Yeah, it's probably got some other kind of little alloy type things, but whatever the chemistry is here, the nodules are kind of put on. Mm-hmm. But it adds a bit more roughness on it. And when they treat the drum side, this is what the little nodules look on it, because that's fairly smooth anyways. Mm-hmm. These nodules kind of look more flat. Mm-hmm. When they treat the drum side, this is important. When they treat the drum side, that's what they call reverse treated foil, okay? Or RTF foil. When you see RTF foil, that means they put the treatment on the drum side of the foil. And it kind of is evident, sort of like in this picture here. It's talking about oxide and oxide alternatives, but before we get into that, the nodule, the treated side of the copper is always bonded to the core material in your laminate.
Nodule, what was nodule?
The nodules, that treatment process.
Okay.
Yeah, that's what they call the treated side. Those little tiny nodules are always the side that gets bonded to the core. So your laminate supplier, like Isola, for instance, when they make the double-sided laminate, the treated side of the foil gets bonded to the core, and the drum side is on the other side of it. Now, after you've put your artwork pattern on and did all the cores in your stack up, and now they want to glue all the cores together before they put the prepregs on, your board shop now will roughen the drum sides on each side of that laminate before they do it. So during the fabrication, the untreated copper on each side undergoes a roughening treatment. So they have this oxide or oxide alternative. That's in red here. Your board shop does that treatment to all the cores that they have before they laminate.
So it can stick a little bit better.
Yes, exactly. So they do the treatment on it. And there's different types of treatment. There's oxide treatment and oxide alternative treatments. So for years and years, they've used oxide treatment, but they had sort of reliability issues with oxide. But they've gone away from it. But typically for, the oxide treatment that they put on is virtually non-conductive. And what happens is they grow oxide crystals to roughen the surface. So it's kind of like making it rust in a way, right? And it doesn't significantly alter the copper surface profile because they're non-conductive, and they just kind of grow the crystals on it, and that gives that roughening edge. But because they had issues, they have now what they call oxide alternatives. And within the oxide alternative, they have two different versions, an etch version, and now they're coming up with a non-etch oxide alternative.
That's like glue?
Yeah, in a way. But the etch treatment is mechanically, they kind of etch it, like they have like an acid treatment, and it actually makes the copper rougher itself. And it does significantly alter the copper surface profile. The non-etch is a chemical bonding kind of to the prepreg, and it does not significantly alter the profile. Okay. And here's, I'll show another picture in another slide, but here's reverse treated foil showing the drum side with the nodule treatment that gets on the laminate. And here is the thing on the matte side before oxide alternative treatments. You can see the matte side. And then after the PCB shop gets through with it, the oxide alternative treatment, the etching one, it kind of has little tiny micro voids in it that help promote, makes it stick better to the prepreg. When they do the RTF foil, it gets a little bit smoother doing the process. These are called macro roughness versus the micro roughness. These bumps get a little bit smooth, so typically around 50 microinches of copper is removed, sort of smoothened out. But at the same time, you have these micro voids that are kind of put into it. So that's sort of what the surface looks like after the oxide alternative etching. And here's a comparison between an etching kind and a non-etch type. So this is what, when we're going higher speeds, people are starting to looking into this to be used on the board shops for it, But that's the difference in the thing. But it all factors in when we're doing our modeling. So I kind of put these numbers in to sort of show it's important that you know what your board shop is using for the oxide alternative if you're doing your modeling and all that stuff.
Okay.
And then this is just a study that I did based on the roughness numbers that they produced. And I did some quick simulation to show the effect on insertion loss between the different samples, and you can see that they're pretty tightly there. So non-etch versus etching, at 14 gigahertz, they're pretty close, so for like 28 gigabaud, we're still able to go with the etching type oxide alternatives, and compared to the non-etch. But if we're going to go now to the 112 gig, we're now worried about 28 gigahertz, and now it's starting to make more of a difference. So we might have to start going with that non-etching kind of oxide alternative, the chemical bonding ones for those.
So does it mean like up to 15 gigahertz we may not need to like worry about the roughness?
Oh no, you have to worry, but it's important what you specify.
Oh, okay, the insertion
Right.
loss, how far you can
That's what I'm
actually
saying.
route your tracks.
Yeah, like what it means is up to 14
Oh, I understand.
gigahertz.
That's relative per inch. Okay,
Yes.
I understand now.
Yeah, we can still get away with the etching kind
If
of
it's very
oxide
short.
alternative, right? But you have to do your simulations and everything work. But you can see that from the study and the numbers that they had, if you kind of had the same geometry and you just changed the oxide on it, that things didn't. This is all in simulation. It doesn't seem to affect it as much, right? So the other thing is recent work that I've kind of come across is the roughness of the plane matters in your stack up as well. Sometimes with thin core laminates, when you have power and ground, you might end up, this is a reverse treated foil that your board shop uses. And reverse treated foil means this side is rougher than this side. And if this is a high speed layer, that you had really smooth copper, this copper on here is a little bit rougher.
And it still may influence your signal.
Yeah, so that's what it shows here. So here's a combination of VLP2 and RTF. So VLP2, when you have the very smooth copper and one of your planes is rough, that's the red, you got insertion loss of 3.4 dB at 14 gig, right? And then if you go to a VLP2, which is, smoother, like if this was VLP2, they were all the same, you get some improvement, as you can see in blue. And green, if you went smoother still, like had a, smoother than VLP2, all of them, you'd have even less. So you've got, 3.4 to 2.6 difference between the smoothest and that. And here's your effective decay, which affects your impedance differences, because the roughness of your copper, because it's rougher, it affects the capacitance between your thing, and capacitance affects decay. So over frequency, you can see how decay is varied. And at 10 gigahertz, this is the difference in decay the traces will see between the two. So that ultimately affects your impedance, because decay is worked into your impedance calculation. This is useful for most people. If we apply my Cannonball Hooray model, just because of the nature of it, some EDA tools that I know of, like Polar SI9000, Mentor Hyperlinks, Z0, Z-Solver, Expedic, these solvers in these tools, they use my Cannonball Hooray model inside the tool. So all you need to provide is the RZ parameter of the roughness.
That's
property.
what you will find in datasheet.
Yes, basically. ANSYS tools and Cadence tools, they ask for SR and R parameters to fill in for the Hooray model, because that's what they have as the Hooray model. And if we use my cannonball hooray model procedure, SR is really this part of the equation. And my cannonball hooray model, because it's 14 balls, whatever, it ends up being a constant. It'll always be 4.9. So for these tools, for SR, you use 4.9. And then they ask for the radius of the sphere for it. And you just simply approximate it as 0.06 RZ. So again, if you know RZ, 0.06 times that, you use that number in the tool. Okay. And then here is Symbior and Altium. They have the same model because Altium have licensed the Symbior solver in it.
They just call it different names.
Yeah, they'll ask for RF1 and SR1, right? RF1 is similar to the one above, except the equation is this part of the hooray equation. But again, it's very similar. You put it in, it'll cancel out. And in this case, you use 8.33 for a constant. And SR1 is the same, 0.06 RZ. So in all these cases, these are popular tools. If it just has hooray, and most of them are just asking you for SR and R or whatever, as long as you know RZ, you can now practically use it.
And this is what will correct the calculations or modeling based on the roughness of the copper.
Right, exactly.
So for very high-speed signals, you really would like to include it because then the results will be more accurate.
Yeah, right.
And that's everything for this video. I would like to say thank you to Bert because he prepared special presentation for this video. And I would like to thank you very much for his time and for his help with creating me this video. So thank you, Bert. And what you think about this video? Did you find it useful? Did you learn something new? Leave comments. If you like this video, don't forget press like button. If you would like to see my future videos, don't forget to subscribe. I would like to thank you very much for watching and see you next time. Bye.